Hello everyone, so today I will share with you how to answer questions number 2. Okay, so in questions number 2, I will share how to solve this question. So let's read the questions first. Draw the stepwise mechanism of the following reaction. So given here a compound which is a secondary alcohol. The name of this compound is methyl 2-methyl. So this is substituent, and then the parent change is cyclopentanol, because there are 5 carbons, 1 2 3 and 4 5, so it will become pentanol due to OH hydroxy group. So we number the first carbon that have OH. So this is become our first carbon, which is alpha carbon, and then this is second carbon, methyl, the one that's bonded to methyl, and it is third carbon, and the fourth, fifth. Okay, then after you analyze the given compound, you will also need to consider the given substrate or another reactants or starting materials. So given that H2SO4, which is sulfuric acid, which is one of the type of strong acid, and then we know this is secondary alcohol, and then will produce more than one products. There are 3 products, so both 3 products are alkene, because the functional group is carbon-carbon double bond. This is carbon-carbon double bond, C double bond C double bond C. Okay, and then we understand all the figure. We will go to answer these questions. Okay, so before you write the mechanism for this for the formation of these products, first product, second product, and then third products. You need to first understand, which is the prior knowledge that you have learnt before in the previous chapter. So the prior knowledge, which is elimination reactions, so there are 2 types of elimination reactions, which is E1, and then also another one is E2 mechanism, E2 reactions. So what is the difference between E1 and E2? The base use, whether it is use a weak or strong base. But in this chapter, in these questions, you will really need to understand the mechanism of elimination, how we eliminate one hydrogen, which is a beta hydrogen, and then other atoms involved in the mechanism. I just want to highlight here that if you have a primary alcohol, then you must to undergo E2 mechanism. But if you are given a secondary or tertiary alcohol, then you must to undergo E1 reaction. And that's all you need to memorize and understand. Okay, so in the previous chapter, in E1 mechanism, which is a stepwise mechanism, there are 2 steps. But for E2, which is a concerted or single step mechanism, there is only 1 step. Everything occurs or happens in a single step. That is very basic and the fundamentals knowledge that you must know and understand. Okay, let's move on to the answer. Mechanism of dehydrations. So I need to stress these things. If you are given a compound H2SO4, then only you know that this is the mechanism name of this reaction is dehydration of alcohol by using strong acids. There is another reactants that we can use to undergo the dehydration of alcohol, which is para. Okay, I don't want to write. I just mention another reactant is para toluene sulfonic acid. So para toluene sulfonic acid is also a type of strong acid that can be used to undergo dehydration of alcohol. Then we proceed with the mechanism. Okay, so mechanism of dehydration. Firstly, I will draw the compound given, which is the starting material. So we have a cycloalkane with 5 carbons. I will make this first carbon and the second, third, fourth, and the fifth carbons. So the hydroxy group, OH group, is attached to the first carbon. Okay. Make sure the bonds is bonded to the oxygen, not the hydrogen. And then we have a methyl group on the second carbon, CH3. Okay, so here I will stress here that at the first carbon, okay, so the first carbon, that there is a OH. This carbon is bonded to OH, so this carbon is known as, we call this carbon as alpha carbon. And then the hydrogen attached to it is alpha hydrogens. Okay, next, the carbon atoms that is bonded to alpha carbon is a beta carbon. Okay, so we have 2 beta carbons. This is the first beta carbon, so I label as beta 1, and then this is the second beta carbon, beta 2. Alright, sorry. Then after you understand all the things, okay, I want to add something. the hydrogen's atom that is attached to the beta carbon, it's known as beta hydrogen. So this is beta hydrogen 1, and then this is another beta hydrogen 2, beta 2 hydrogens. Okay, then we will continue with our mechanism of dehydration of alcohol by using strong acids. Okay, so this is the compound given from the question. Alright, so look at the sulfuric acid. We expand the structure of sulfuric acid become H2SO4 and then showing on this oxygen atom there are two lone pairs, and then also on the oxygen atom in hydroxy group there are two lone pairs in neutral state. The first step is that involve the proton transfer. The oxygen atom, one of the lone pair from the OH group on the oxygen atom will try to form the bonds with another hydrogen atom from the sulfuric acid. So this lone pair will become a bonds here and then forming with hydrogen atom, so that we have OH2 here. But before we can form OH2, the bonds between hydrogen and oxygen atom, which is this one, will be break. Okay, and then all the bonding will be get by the oxygen atom of OSO3H, the remaining. And then what will happen is that we will form H2O, which is water, a good living group. And then this is a side product or byproducts, H2SO4 minus, a base that we will use to react in the next steps, which is this is E1 E1 reaction, so it use a weak base. H2SO4 minus will act as a base. So as a brief conclusion, I can say that in the step 1 there is a conversion of OH to plus OH2, positive OH2, which means that OH is a poor living group, so it will convert into a good living group first. So that this is only the difference from the previous lesson that we learned in E2 mechanism reaction. So this will become the first step, which is the addition to E2 mechanism. Okay. Sorry, E1 mechanism, not E2. Alright, so we will proceed. Okay. In the next step, which is step 2, before we proceed to second step, maybe you guys wonder why we need to put positive sign on oxygen atom, because the bonds around the oxygen atom is more than 2, which means that we have 1, 2, and then 3 bonds. So when we calculate the formal charge, we will get positive ones. So here is the proof. This is the proofs. Okay, we will calculate the formal charge of oxygen atoms. Okay, so the formula of formal charge is that number of valence electrons minus by number of lone pairs plus half times number of bonding, or simply that you can simplify this formula as formal charge equals to number of valence electrons minus by number of lone pairs and then minus by number of bonding, assuming that two electrons in a bonding as one bonding. So for example, this oxygen, so oxygen atom basically have 6 valence electrons, then minus with lone pair. How many lone pairs this oxygen atom have? There is 1 2. Okay, 1. So we have 2 lone pairs, minus 2, and then minus number of bonding. Number of bonding is with carbon 1 bonding, and then with another hydrogens 2 bondings, so total 3 bondings. So 6 minus 2 minus 3 will get positive 1. So because of this, the charge of oxygen must be positive on oxygen atom. Okay, so we proceed onto the step 2. So in step 2, it is very simple and easy to understand because there involves the formation of carbocation, which is our positive OH2. The bonds between this carbon and oxygen, which is C carbon oxygen bond, will breaks. So this is we call as the heterolysis of CO occur. So forming a secondary carbocation. Why secondary? Because there is 1 and then 2 neighboring carbon attached to this carbon. So it is secondary carbocation, and then the OH2 plus OH2, positive OH2 will leave as the water as a good living groups. Okay, and then I just want to add a little bit of information in this step, which is step 2. It is a crucial step and one of the important step, because this step involved is known as the rate determining step. Because it only involves the bond cleavage or heterolysis of carbon oxygen bonds. Rate determining step. Okay, and then we will look at the last step. Okay, so in the last step, our H2SO4 minus, we will draw like this in expanded form, OSO3 expanded hydrogen, OSO3H, and then the minus or negative charge is labeled on the oxygen atom. Please do not miss this. This is very important. And then we'll show there are 3 lone pairs on oxygen atom from H2SO4 minus, and then one of the lone pairs will be used to form the bonds with the hydrogen atoms, which is a beta hydrogen, from the carbocation formed previously in the step 2. So in this case, I'll show the beta hydrogen one, which is this hydrogen, the blue one, drawn in blue color, light blue color. So lone pairs taking the hydrogen atoms, and then the bonds between hydrogen and carbon, CH bond will broken. So that will lead to the formation of double bond here, carbon-carbon double bond, which is alkene. A new pi bond is formed. So this is how the first product is formed. And then for the second products, why the double bonds is formed here. Okay, so we will look at the beta hydrogen 2, beta 2 hydrogens. Okay, and then the same things, the lone pairs on oxygen atom from H2SO4 minus will trying to form the bonds with the hydrogen atoms with the beta 2 hydrogen from our carbocation, and it will take as H2SO4 minus, and the bond here also will cleaved or broken. The heterolysis of carbon hydrogen atoms, carbon hydrogen bonds occur, and then forming a new pi bond here. Basically the same thing, and then because of this, why the double bond forming here. Okay, and then the last or the third product, how it formed. So basically the third product is formed due to the rearrangements, which means that our third product, which is this product, is formed from the rearrangement. So this is known as the rearrangement product or rearranged products. Okay, basically this is our carbocation form in the second step. Sorry, this occur again, but you need to show one hydrogen atom, so just draw like this expanded structure. And then why this is still become a carbocation here, because at this carbon there is only 3 bonds, it is not octet, 2, 4 and then 6. Okay, so this type of carbocation is tertiary carbocation because neighboring carbon is only 2. Okay, so we will expand one hydrogen here, and then we can see that we observe that the arrangements may occur or can occur. So we will shifting this hydrogen to the carbon carbocation, which means that this is a adjacent hydrogen atoms will be shifted to carbocation here. And then next thing what happens is that okay, what happens is that this will become CH2 already octet. But now here this corner or this carbon is not octet, which there is only 2, 4 and then 6. So will become a carbocation here. So what type of carbocation is tertiary carbocation? Because there are 3 surroundings carbon atoms, 1, 2 and then these 3. So 3 neighboring carbons will lead to the is known as tertiary carbocation, which is more stable than secondary and primary carbocation. So after we rearrange the carbocation, our tertiary carbocation will undergo um, okay, this is our base H2SO4 minus will remove a, another hydrogen atom from our carbocation, and then will lead to the formation of a pi bond, a new pi bond. So here is okay. I think this is not beta 3 hydrogen, sorry. This is uh, just hydrogen atom. So one of the lone pairs from H2SO4 minus on oxygen atom will be used to remove this hydrogen atom. So it will form the bonds, and then the bonds between carbons and hydrogen is heterolysis or broken, and then the bonds will transfer to here, forming a carbon-carbon double bond. So these are the final products, or the third product. The double bond will form here, and then the CH2. So you can see all the things. Okay, I think that's all for this time video. If you have any questions to ask me, do not shy to comment below in the comment sections. Thank you, and see you in the next video. Bye.